is that's all right. All right, so today we're going to start our discussion on organometallics. And that discussion is going to rely heavily on an understanding of covalent bonds, dipoles, nucleophiles and electrophiles. Like all of that is going to be tied up in organometallics as well. Like those are concepts you can't get away from. So what an organometallic is, it is a species that has a carbon metal covalent bond. So this is a carbon metal covalent bond. And you might ask, like, what does this have to do with alkyl halides? Well, alkyl halides are one of the main precursors to the synthesis of organometallics. So we talked about synthesis of alkyl halides, whether it's taking an alkene and adding HX to it, or taking an alcohol and converting it to an alkyl halide, or doing a allylic bromination. So now this is the application. So let me kind of map that out. So we had alcohols to alkyl halides. We had allylic bromination. That led to alkyl halide. And then we also did in part one, I'll shrink that down some. In part one, when we talked about, let me just draw it out. We had alkenes plus HX. All of these are ways to make alkyl halides. All right, so with those alkyl halide methods, we can take the alkyl halide and actually apply it. So that's what we're doing now. So these are synthesis methods. Now we're looking at applications. And one of the key applications that we're going to look at is going to be taking those alkyl halides and using them to make organometallics. Right. So if I take an alkyl halide, RX, everybody okay with that? The X is the halogen.
Yes.
I'm just abbreviating this just, for the sake of brevity. And then R is the alkyl part. Right. And as you can imagine, this is a highly polarized bond right here. Right. This is going to be polarized towards the halogen, because the halogen is typically more electronegative than carbon. Right. And if I take that alkyl halide and I react it with some metal, right, I'm going to generate what's called a organometallic. Let me switch pens. Sorry, I had to put my dog out. So we'll have an R metal bond, and then that also and then the halogen that was here is still here, right? And depending on what type of uh, organometallic you're making, that's going to determine what the halogen does. It either stays associated with the metal or it ends up with another metallic species. We're going to talk about that. So the metal carbon bond, I'm just going to write this here. So CM is now, instead of the bond being polarized towards that halogen like it was over in the starting material, now this is actually polarized this way. So the carbon is partially negative and the metal is partially positive, right? So alkyl halides, I'm sorry, organometallics, which is what this is, they're excellent nucleophiles. Excellent nucleophiles. So when they react with electrophiles, it's the carbon part that's used as the nucleophile. So it's the you can see the polarity. You see that the carbon is partially negative, and so anytime, excuse me, you put a organometallic in the presence of an electrophile, it's the carbon that's going to be your nucleophilic uh, atom in that carbon metal bond. So carbon is nucleophilic. So that the carbon is what's going to supply electrons to whatever electrophile that organometallic reacts with, right? And again, that is a covalent bond. So there's a shared pair of electrons between the carbon and the metal. All right, so these are, again, great nucleophiles, and they react with electrophiles rapidly. They're also very sensitive to water. So anytime you put a organometallic in the presence of water, it's going to destroy it. So it has to be kept anhydrous. Right, no water. So let me show you exactly what happens. So if I have a organometallic and this is partially negative and this is partially positive, and I react that in the presence of any proton source, really, but water or any proton source, but we're just going to use water. Right, what ends up happening is the carbon gets protonated. Right, so the hydroxyl group from water ends up with the metal, and then the carbon gets protonated. This is bad. This is like not what you want to happen when you have an organometallic. So no water, no proton source. Anytime you put this in the presence of water, it's going to destroy your organometallic. So water is just going to do proton transfer, and your organometallic that you spent all day making in the lab is done. Right, it's gone. So you want to keep this dry and anhydrous. So you got, when you make it, your solvents have to be distilled and dried, and it has to be sealed up so no moisture can get into the reaction vessel. All of that. All right. Any questions so far? So again, the way that this all fits together with alkyl halides is we talked about ways to make alkyl halides, and now we're talking about one of the ways that you can apply alkyl halides, which is to use them to make our organometallic compounds or complexes. And the other part about the organometallic is that, when you use it, when you take that organometallic, is really mainly used in the formation of new carbon bonds. So we're going to talk about that, like how these things react as well. So organometallics are precursors to new carbon bonds. Right. So that's a way. It's one of your reactants in a carbon bond forming reaction, and we're going to talk about several of those. All right. So for this class, we're only going to talk about two organometallics, well, really three, but two that actually get used to make carbon bonds. So we're going to talk about granules. So we're going to talk about granule reagents. So let's just say this is what we call a granule. So a granule reagent. And then the other organometallic that we're going to talk about is copper based. I'm just going to use methyl here. This is what we call a Gilman reagent. Another name for it is a cuprate. All right, so these are the two organometallics that we're going to be talking about, and how to make them, and also how to use them. All right, so let me show you the use, and then we're going to get into more specific, some more specific reactions. So with the Grignard, if I take that, and normally the way you make these new carbon bonds, because again, organometallics, the main use for them is to make new carbon bonds. Normally, the way you do that is to take the organometallic and react it with an alkyl halide. So let's say I react this with methyl iodide. Right, that's actually going to give me, let me change the color of that methyl group so we can actually see what's happening. So that's going to give me on the other side of the arrow this new carbon bond, right? And we'll talk about how the reaction happens and all that stuff. And then so it'll be that. My H's are just not cooperating today. Right, so this is the new bond right here between the two carbons, and then what's left over is the iodine with the metal, so it just make a salt with the metal. Right, we'll talk about how this works and the mechanism and the arrow pushing and all that stuff. So that's one reaction that organometallics do. You can couple them with other alkyl halides and make new carbon bonds like that. Right, and the cuprates react much the same way. You can take this plus, let's just take the same thing, methyl iodide. Let me just copy it. right? And then you're gonna make a new carbon-carbon bond on the other side of the arrow. All right, so that's the main product, new carbon-carbon bond right here. And then what's left over is the cuprate itself. So that's going to be that plus lithium iodide plus right this copper species. Right, and if you notice here, only one of these groups. Yeah, let me be black. Only one of those groups got transferred to make that new carbon-carbon bond. Right, so when you're talking about organometallics, their main use is to make carbon-carbon bonds. You use them in different synthesis reactions. You might use it in a total synthesis to make a larger molecule, or you might make a fragment of a larger molecule. All of that's what, but that's the main use of organometallic compounds, is to react them with some other species to give you a new carbon-carbon bond in the product. All right. Any questions about this part or anything we've talked about up to this point?
No questions.
All right. Um, all right. So let's talk about the Grignard reaction. Give me 1 second. All right. I actually don't want to use that. Let me just put another page in. All right. So with the Grignard, we're going to talk about how to make those, and we'll go through the mechanism of how to make it. So with the Grignard reagent, and let me put this handout in the chat again. For those who came in a little bit after I uploaded it. All right. So with the Grignard, you have again an alkyl halide. You have magnesium metal. And when you react those two together, this has to be under anhydrous conditions. So you have to have some inert aprotic solvent. So in this case, it's ether. So this is inert aprotic. Cannot have a proton source around your organometallic, because if you do, again, it's just going to do proton transfer with the solvent and it's done, right? It's a total complete waste. All right, so then this is your Grignard. If you notice, the charges are now different. Again, the carbon part of the organometallic is partially negative, and the metal is partially positive. right? And then the halogen is just kind of hanging out here, is making a salt with the metal, right? So when you take these, and let me add another. Yeah, it's actually -78. The temperature has to be kept cold as well. So it's at -78 degrees Celsius. Very, very cold temperature. Dry, you basically make a bath with dry ice, and you pour acetone over it, and that'll bring that reaction down to that temperature. All right. So again, this is your granule reagent. Now let's look at how this works, right? So we take the granule. This is the mechanism. So the first part, and this is, even though it's radical, it doesn't go through a radical chain reaction. Right? So it's a radical mechanism, and that it involves one electron homolytic and homogenic bond cleavage and bond making, but it doesn't go through a chain reaction. So it's not like a initiation, propagation, and termination, but it is a radical mechanism. So as you can see here, the first thing that happens is magnesium, which is a group 2 element. It has 2 electrons. It donates 1 electron, and let me put some electrons in here so you can see this for what it is. Right, so that halogen already has 3 lone pairs. So then you homolytically cleave the RX bond, right? And so now you make a carbon radical, and then your magnesium now has a +1 charge because it gave 1 electron away. And then the halogen is here, right? Kind of like still kind of like a salt with magnesium. So on the first step, this is cleavage of the RX bond, and it's homolytic. Right, and what facilitates that cleavage, I guess you can say that magnesium is kind of the initiator, because it gives 1 electron to the halogen to facilitate breaking that bond. And then down here, now the magnesium and the carbon, or the alkyl part of that alkyl halide, combine. Right, so that's where your covalent bond comes from. It's from this radical reaction right here between magnesium and carbon. So now this is, go ahead.
For the halogen in the first reaction, the products on the product side, it gained 2 electrons.
No, it only gained 1. It took 1 from the bond, and it got 1 from magnesium. So that gave it 4 lone pairs. It already had 3. So it had
So it
3.
gained 1 electron.
No, so here, let me show it to you this way. So if I have this, and I break this homolytically, I'm going to have this. Let me put it on the other side. Is that right?
Yeah.
And then the magnesium, if that gives away, not to make a bond, but just donates 1 electron to the halogen, then the halogen ends up with, it has 7 here, but it ends up with 8 after magnesium gives it that electron. And then you end up with this plus R dot plus Mg dot with a plus charge on it. And then now this is negative. So it had 3 lone pairs. It took 1 electron from the bond, that gave it 7 electrons, and then magnesium gave it an electron, so that gave it 8. So that's how it has a -1 charge.
Oh, okay. Okay.
All right. All right. So now we see how that carbon metal covalent bond is formed. Now with the granules, we're going to talk about some reactions that they do, namely coupling reactions and additions to carbonyl. So we're going to talk about the coupling reactions first, and then we're going to go back and talk about the copper cuprate synthesis, and then the reactions that they do. All right, I don't need this page. Hold up. Well, actually, I do. I'll leave it. So we're going to say, all right. So with the organometallic reactions, let's talk about what I like to call these coupling reactions. Right. So with the coupling reaction, I'm going to give you a generic um, illustration, and then we're going to look at some more specific examples. So one of the reactions that organometallics can do is coupling reactions, and then they also can do carbonyl additions. All right, but for the coupling reactions, if I take an organometallic plus some alkyl halide, where X is a halogen or a good leaving group, there are other groups that can act in that role as well that are not halogens. So X is a halogen or a good leaving group. What we do in this case is, right, end up reacting the carbon and the R group or the alkyl group of the alkyl halide, and then the metal and the halogen end up as a salt, right? So when we do this reaction, we end up with a bond between C and R. So this is my new carbon-carbon bond that I make. And then we can just say plus MX. Now, what MX is going to depend on what the organometallic is and how it reacts, right? And then with the carbonyl additions, it's the same, it's similar. So because the carbon is the nucleophile, so it's CM plus, let's say aldehyde. So when you react those two together, right, the carbon is going to attack the carbonyl, and then you'll end up with an intermediate that looks like this. So there's the carbon that attacked. And then the final step here will just be to quench it. So this C attacked the carbonyl. Right. So with these carbonyl addition reactions, this is a way to make alcohols out of from organometallics and carbonyl. So this is a method for alcohol synthesis. All right, so it's an alcohol synthesis method. All right, so let's talk more about the coupling reactions. And let me see what what we have here. We got both. I'll come back to the cuprates. So let's talk more about the coupling reaction. So again, when we take the organometallic plus some alkyl halide, we're going to react those two together, and we're going to make a new bond between C, the carbon group of the, or the organo group of the organometallic, and then the R group of the alkyl halide that it's reacting with. All right, so let's look at the next, a real example, right? So for these examples, this is the strategy. The strategy is to identify your organometallic, or CM, and then identify RX. Right, your alkyl halide. So let's look at we're going to look at the two reactions here, and then we'll come back and introduce the Gilman and talk about how to make that, and then we're going to come back to these reactions and look at the two in the middle. All right, so let's look at that first example. Where is in that example, where is RX?
Is it the second one?
Yeah, you always, if you want to identify RX, just look for the halogen or the leaving group. So this is X, and then this right here is R. So that's my RX piece right there. Once I identify that, by default, the other reactant has to be CM. So this is carbon, that's the magnesium metal. So this is CM. Now the mechanism as far as how this happens, it can actually, that's more than one plausible pathway. But let's suffice it to say that a reaction like this is going to be like a substitution. And so we could even think about the metal, the iodine from here, because it has lone pairs, kind of coordinating with the metal, and then the substitution happening that way. And I can show you that, but let's just go and figure out what the product is, and then we can come back and talk about that. So there's going to be a bond made between this carbon and this carbon, right? So if I were to just draw the arrows mechanistically from here to here, right, there's going to be a new bond there. So my product is going to look like this, where I have the aromatic ring that doesn't change. I have a carbon here. I'm just going to put a dot right there for that carbon. And it has a bond between itself and another carbon here. And that carbon is bound to, right, so this is now CR. Right, anybody not see that or have a question about it?
So the dot on the left is what?
It's this carbon, the carbon right there that's highlighted in blue. This one.
Okay.
Right. There's a very real temptation to just fuse the two together, but you have to show that bond between those two carbons. And I say that because since as long as I've been teaching this class, there's always a temptation to do this, right? So take this and then just draw it like this, without the carbon-carbon bond between. right? And this is not right. You can't just fuse those two carbons together. You understand what I'm saying? So you have to show the bond. I drew it out like this on purpose to kind of highlight the fact that you have a new bond between those two atoms.
Okay.
Yeah. It never fails. Every time I teach this section, there's always somebody who wants to take the atoms and just fuse them together, and that you can't do that. All right. So this is also kind of illustrative of the types of groups that you can use to make the granule and the groups that you can react it with. So for the granule itself, let's see if I have room, I can shrink that. Well, I'll go back and talk about that. All right. So that's the reaction between those two. Let's look at the bottom reaction. Let's see if we can figure that one out. First, so we want to identify CM and we want to identify RX. The easiest way, in my opinion, is to find the metal, right? And you know that magnesium is going to be your metal. Right. So once you find the metal, then you look for the carbon that's bound to it. So where is that?
Right.
It's right here. So that's magnesium, and this is the carbon that's attached to it. All right. And over here, I can also find RX, right? This is the halogen or leaving group, because it's not always, it doesn't have to be a halogen. There are different types of leaving groups that can work here. But since we're talking in the vein of alkyl halides, then we're going to, we kind of narrow it down to that. And then this is the carbon that's attached to that. So this is RX. And then this is CM. So in the product, what is that product going to look like? Anybody want to try to draw that in?
I can try.
Go ahead. You must not have your stylus.
I don't.
I can tell. I can tell.
My computer.
It's all right. Take your time. We good.
And then, oh no, wait.
Okay, good. So that's the carbon that's reacting. Good. Mhm.
Like this, and then is that right?
Let me see. I think you have one too many carbons in there. So erase that blue bond on the right, that single bond you have to that dot, and just move that. You can just move that piece over, and that'll be sufficient. Yeah, so put the dot back in.
Okay.
Okay. Yeah. So that's the carbon right there that's highlighted in pink. Right. So then everything else, so if you draw a bond from that carbon up.
Oh, okay.
Mhm. You have one too many carbons, but the bond is fine, but you just have one too many carbons in there.
And then do that.
What's left? Yeah.
Oh, that right?
Yes. So you'll have this, and then this is bonded to this, which is here, like that. So you see the two carbons coming together right here. And then that is in addition to this MgBr Cl, but this is trash. Right? You can't do anything with that. You get rid of that in what's called a workup. You just add a aqueous solution to quench everything, add some more ether, and then extract out the product in a separatory funnel. So yeah, that's good though. We're actually gonna stop here. I don't want to
Um,
go ahead.
Uh, so can you scroll back up to the first problem? So the R is the alkyl
Yes,
carbon.
it's the carbon part of the alkyl halide. Yes,
Okay.
and it's all and in this, I try to simplify it because here is like whatever carbon is bound to the halogen, that's the reactive site. Everything else is just a substituent, is attached to that carbon. But the reactive site is where the halogen is. So that's where the reaction is going to take place between that carbon and the carbon of the organometallic.
Okay.
All right, so this doesn't happen it doesn't happen on any other location. That's why you have to identify the Rx as the location of the reaction. So it's that atom bonded to the halogen. That's your reactive site. Because again, this is all based on dipoles. So right here, let me go back to here. This carbon is partially negative. This is partially positive. For this one, this is partially negative, and this is partially positive. Right. So that's where the reaction is going to take place between the carbon that's partially negative and the carbon that's partially positive. It all goes back to nucleophile, electrophile chemistry. This is your nucleophile. This is your electrophile.
Okay.
So the site within the nucleophile where the reaction takes place is generally the most polarized bond. And in this case, it's the bond with iodine.
Can you repeat that again?
About what? The
Like
electrophilic site?
the most polarized.
Yeah. So the in the electrophile, I'll just write it out.
Okay.
So the electrophilic site come on, Russell, tighten up. All right. So anytime you have an electrophile, the site where it's going to react is usually the most polarized bond. So that polarized bond between carbon and iodine is where the reaction is going to take place.
Thank you.
Mm-hmm. Any other questions? All right, I'm gonna stop here, stop recording.